Hey, welcome back. Acceleration, highly important. Essentially in physics, if we're looking at motion, we're evaluating, we are measuring, we are quantifying, we are looking at acceleration. We are looking at how something is changing its velocity in a certain amount of time. And so we're going to find that as far as acceleration goes, there are things that we have to decide whether something is constant, whether or not it isn't constant, and we always need to keep in mind things like direction. Let's just jump into the video and take a look. Got a few interesting things for you. Got some problems for you to work on as well. And then don't forget to check out the other video that will have some other practice problems, and definitely work on those problem sets that I have for you. Let's take a look at acceleration. All right. Welcome back. Let's talk about acceleration and how that pertains to what we've been talking about with motion, and we're looking at particularly just what's going on along just basic horizontal motion at this point, right? Gotta get that pick me up. So acceleration here, I've got some slides set up, some pre-made questions that will kind of help us organize our thoughts and help us get going from this. Kind of center what we know into understanding acceleration. I don't know what I mean by center by this. I'm just kind of rambling. Been a long day. Let's jump in. So we see here, I just put a little bit of notes here for you. The acceleration, just the rate of change. So pretty much everything about motion is understanding the relationship with rate. What is happening? Whatever it is you're starting with, it'll either have to do with position in time or some pre-existing motion in time, or lack of motion per some unit of time, right? So if we're talking about acceleration, right? So it's the rate of change of the velocity, and so how fast, right? How fast over time? What's the change in velocity per some unit of time? That's what we're really looking at. That's what when it says in respect to time, that's what it's referring to, right? Let's go with a smaller stylus point. All right. So let's express the concept of average acceleration of an object. All right. So we've got acceleration, and that's a lowercase a. Okay. Capital A is something like an angstrom. Something else later on. So we've got average acceleration, right? Well, if we look here at this graph, then we realize that this is a basic linear relationship, and velocity being a function of what time is, right? So we know that this would be equal to the change in velocity over the change in time. And then, of course, this looks like a basic slope type setup, so we know that we would have a final minus initial velocity and a final time minus an initial time. And that's basically it. That's the concept of an average acceleration, right, of an object. The acceleration is not necessarily always average. We're going to find in some upcoming units and concepts and lab stuff that we're going to be doing that for it to stay an average rate, there's going to have to be some sort of input, and that's where we get into forces and things of that nature. Okay. So discuss the conditions for a change in an object's velocity with respect to an increase, decrease, or a constant condition, right? And so it's a lot of physics is about conceptual thought. The difficult part is not the plug and chug, taking the value of a variable and plugging it in. It all is about thinking about the condition, and let's see what is happening with this under these conditions, right? So we're going to just take a look at what happens if there's an increase, a decrease, or basically nothing really changes as far as the velocity goes, right? As far as acceleration goes. So if there's a change in velocity that increases, And this is just how I like to think about it. I like to use shorthand notation, right? So we're going to have a condition that if the velocity decreases, and then let's sort of think about a situation where the velocity is constant. Well, if the velocity is constant, then we can just say we can set that equal to 0, right? Just kind of set this off with commas. If this, then what, right? So then acceleration, right? Then something's happening with the acceleration, right? So, and then keep in mind under this condition right here, right, that under this condition we are talking about it being constant, okay? We're talking about that this would be constant. If that were the case, then the acceleration, we might think of that as 0 because it's constant, so that kind of fits, right? So if we have an increase in velocity, if we go back up here to our graph, if we have an increase in velocity, well, if we were here and now we're here, well, we can see that this has a positive slope, so that would have to be a positive acceleration. So the acceleration would be positive, right? It would, well, let me do this. The acceleration would equal some sort of positive value, right? And then right here, our acceleration, if the velocity decreased, if, say, we were here and then it goes in this direction, right, then obviously negative slope, so we would say that our velocity is negative, right? And I'll just put some quotation marks around that just to sort of set that off. So now, and again, this, what I'm doing, it's just shorthand notation. This is just a way of organizing it. I've never seen it this way in a book. Instead, I could write out complete sentences, but if you put things in an organized sort of fashion like this, I think it makes it a little more convenient just to think about what's going on, right? Okay, so let's think about this. We've got, if we look at our graph, delta V over delta T, we already know from right here on the graph where we've separated out kind of with the point with the VF and VI, that there's really two points we're looking at, kind of a beginning and an end, right? So if we think about it, we have to ask ourselves, what's the relationship between the final and the initial velocity at each under each of these conditions? Okay, that's what we're wanting to think about. So if it's constant in the middle, if the velocity is 0 and the acceleration is 0, then we can say that this point and this point here, we would have something that is more like this, a straight line. So if we have a change in velocity, a change in time, then obviously it's constant. So right here we would say that the final and the initial, they're of equal value. They equal each other, all right? So that velocity isn't changing. It's at 0, so obviously it's not accelerating. Now there are other conditions we're going to look at. These are just the basics, all right? This is just sort of the basic fundamentals of that. We're going to find that there are some conditions where something could happen, and we could maybe, I don't want to say disprove this, but we're going to find there's some other conditions that can occur where we can alter this just a little bit. So right here, this first one, if the increase in if the delta V, if it increases, right, then what does that mean about the final velocity? Well, if we go back up here where we had this, right, where we had this part right here, then we know that this right here is our final velocity, and this would be the initial velocity for the data set we're looking at, right? So obviously there was an increase in the final velocity compared to the initial velocity, which means that when we have the negative acceleration down here, that the final velocity has to be less. And we can see that up here, right? We can see that with this negative slope, that right there, this would be the final velocity on this one, and the initial velocity would be there. And so that kind of makes sense. I love that afternoon cup of coffee. Instead of French roast, I'm going back to some Italian roast. I forgot how much I kind of like Italian roast as well. It's a nice little change. Sidestep. Let's move forward to another idea, another concept, and see what we've got. Turner's treadmill. I can't remember where I got this problem from. I probably found it in a book years ago. I just don't know. So Turner's treadmill runs with a velocity of negative 1.2 meters per second and speeds up at regular intervals for a half-hour workout. So that would be 0.5 hours, right? So after X amount of time, after 25 intervals during a half-hour workout, right? After 25 minutes, the treadmill has a velocity of negative 6.5 meters per second. What's the average acceleration of the treadmill during this period, right? So the first thing you always want to do is just write out what you're given. What are you given? Let's go back here. I don't like the way that G looks. What's our given information, right? And so we have delta t. So we're told 25 minutes, right? So then we've got two velocities, right? We're told that we have negative 1.2 meters per second, and we're told we have negative 6.5 meters per second. The treadmill has after at the 25 minutes, it has the negative 6.5 meters per second. So afterwards kind of sounds like the final, right? So we've got a final velocity of it's negative 6.5 meters per second. So we have an initial that is the negative 1.2 meters per second. Negative 1.2 meters per second. This is not difficult math, but I have noticed that what people tend to do on this is they always ask, hey, what do I have to do with the seconds and minutes so they don't match up? Well, obviously you need to convert the time unit to seconds, and here's where old chemistry skills, if you've had a chemistry class, and I imagine you probably have, and that whole dimensional analysis, stoichiometry thing, that doesn't go away. None of that goes away. Dimensional analysis is a part of everything. So we just need to analyze this. You know, we've got so many minutes, so many seconds. We know that at 1 minute there's 60 seconds, and so see that 0, 6 times 5 is 30 is 12, so that would be 1,500 seconds, right? We got 1,500 seconds. Let's press on. All right, so now at this point we just need to plug and chug. So we've got an average acceleration, which would be the delta V over delta T, which we know is the final minus the initial. And there's a final minus an initial time. It's just what we're assuming is what we have to assume is after 25 minutes, so the clock started running now, and then 25 minutes later it stopped. And so in this situation, and in a lot of situations, the way we measure time when we look at a condition, we assume that the starting point is at 0, but that may not always be the case. We're going to find that we can analyze an object that's in motion at different points of time within that motion, and so the initial time would not always be 0. It would be whatever it was at that point of time in its motion. Okay. So we've got just delta t. So I'm not going to bother to write delta tf minus ti, right? And so we subtract this out. So we've got negative 6.5 meters per second minus the initial velocity minus negative 1.2 meters per second. And so you can see that you've got minus a negative value, which means basically you're going to add those two together, right? And it would help if I finish out the fraction. I get ahead of myself sometimes. All right. And then divided by time, so that was 1,500 seconds. So 6.5 minus 1.2, that'll give us what, 5.3. No difficult math here. And of course that is meters per second, and that's divided by the 1,500 seconds. So you should be able to see that the seconds unit will cancel out, right? Okay, you're going to have to forgive me. I'm sitting here editing this video to be able to upload it, and I've realized that I completely misspoke. It never even once occurred to me that I misspoke. Meters per second is meters per second squared. What I was thinking when I crossed out seconds, I have no idea. I didn't catch it literally until just now when I'm editing this video to upload it. So instead of redoing the entire video, I'm sitting here drinking a cup of coffee and begging for your forgiveness. I promise you, I know that meters per second is meters per second squared. So if you can just overlook this one little oversight on my part and share just a little bit of forgiveness, I would definitely appreciate it. Let's go ahead and get back to the video. Hopefully there's no more mistakes. Bye. So now we've got 5.3 divided by 1500. Plug that in and we get something along the lines of 3.5 times 10 to the negative third meters per second squared. Done. It's pretty easy, right? And that should be a negative value because this up here is negative. I tend to forget my negative symbols a lot when I do this, so always double check. So you saw that I kind of did the math in my head as far as that goes, but then as I did that, because I wasn't being careful, I forgot to carry down my negative symbol. It's a good lesson. It's a negative 5.3, so this would be a negative 3.5 times 10 to the negative 3 meters per second. And it makes sense that it's a negative value because it says it runs with a velocity of negative 1.2 meters per second, and then after 25 minutes it's running negative 6.5. So remember, acceleration has velocity in it, right? So when we're looking at acceleration, we're looking at a change in velocity. Well, velocity we know is a vector unit. Vector involves direction, and so the negative symbol here involves the direction in which it's turning. So you can think of clockwise, right? So I'm doing this kind of clockwise for me, but I'm trying to do this on the screen so that you can see it clockwise, right? So when you think of clockwise, that's positive. When it's going in the opposite direction, we think of that as negative. So this thing is moving in a so-called negative direction mathematically, right? But it's just moving in whatever direction it was built. All right? Let's do another problem. All right, we got a passenger train. So that means I got to draw a train. So let's see here. All right, we got a passenger train. Don't laugh at my train. So we're going to have a train here. Let's put some windows on this thing. I know. Those are some pretty crooked-looking windows. Those are kind of better. Let's put some stripes on this thing. Let's make it look like a sporty train, right? And then I don't know. That made it look worse, didn't it? We're going to call that a train. All right. So passenger train is traveling on a straight track with a negative velocity and a positive acceleration. All right. So if it's traveling with a negative velocity, I keep hitting that down there. If it's traveling with a negative velocity, all right, then and a positive acceleration. Positive acceleration means it's moving forward. And so now, is this thing speeding up or is it slowing down? Is it speeding up or is it slowing down? So we've got a positive acceleration but a negative velocity. So even though something is moving forward, you might still be going forward, but let's say you trip for whatever reason, or somebody pushes you, for a second you will accelerate forward, but then as you slow down, you are still accelerating forward because you're changing your direction. Then for that reason, what that means is our negative velocity, what that means is it is slowing down. That's all that means. Positive acceleration means it's moving forward. That's really it. It's just again, just something, just a conceptual problem. All right, Carlin is out for a ride. I don't know where I keep finding these things. Carlin's kind of a cool name. All right, she slows down on her bike as she approaches a group of hikers on a trail. Explain how her acceleration can be positive even though her speed is decreasing. This is similar to the other problem. Just want to maybe try to quantify it a little bit, and let's see what happens. So again, don't laugh at my got some wheels. Let's see. So and then let's see. There's a seat here, right? So be sitting on that, and then there's some pedals there, kind of leaning forward. So we're gonna need handlebars on this thing here, right? It's not too bad. It's not too bad. So let's get a ground here, and so we've got a change in velocity, and as she approaches, explain how her acceleration can be positive even though her speed is decreasing. So by speed, in this situation, it means velocity. So the speed is decreasing, so what that means is a negative direction as far as the speed or velocity goes. That's what that means. Okay, and then we've got the acceleration, all right, change in acceleration, and that is going forward, right? So that is also in a positive direction because she's going forward. All right. So let's think about this in terms of the final and the initial velocity. This is what I like. This is what I think is helpful. So the magnitude of the final velocity, according to this, would have to be less than the initial, right? So I like to just grab some numbers out of thin air, and the number 1 is an easy number to work with. So if we think about this, and we know that from up here that the direction is a negative direction as far as velocity goes, then I'm just going to use the number 1. Why not? Because 1s are easy to work with, but the final velocity is less than the initial, so let me just come up with another number, 2. 2 is just greater. This technically just means that the initial was more negative. That's all that means, right? So now let's just plug into something here. We've got delta V over delta T. So that's VF minus VI over delta T, right? So whatever time is, it doesn't matter. All right, you can put a 1 down here or just put delta T, right? We can put delta T. So I'm just going to put delta T. Put a 1 if you want. So our final velocity is negative 1. That's the value we're assigning it. This is minus the initial. So it's easy to see here that we've got minus a negative 2. So basically we're adding 2 to it, right? We're going to subtract that out. So that's going to give us 1 over delta T, which we can see that there's a positive acceleration because of the direction she's going. And it makes perfect sense. Mathematically, it works itself out. And that's it. Let's just stop here. I'll do another video with some other problems where we're going to derive some really large equations based on these concepts. Or not really large, just some other stuff. It was good seeing you again. Look back through this. Make sure you get that in your head that acceleration, it's a change in the velocity, but it also, because it's a vector quantity, has everything to do with the direction of the motion. So if the direction changes, even though it's a constant rate of change, there is a change in acceleration. It is accelerating because it's changing direction, right? Because of the whole vector quantity thing. It's good seeing you. Bye. And there you have it, acceleration. Don't forget, when it comes to acceleration, that you're looking at direction. Direction is always very, very important. If direction is changing, even though that velocity may be not changing, constant, you've got a change in motion. So you've got a change in acceleration. So think about like a merry-go-round. When you're a kid, we tend to, you play on a merry-go-round. If it were to spin at a constant rate, one might think, well, it's not accelerating because it's moving at the same speed over and over again. But because as the object U is turning and changing directions, there's technically acceleration that is occurring because there's a change in the direction, a change in the vector, essentially. So all that, you have to keep all that in mind. Those problems that we worked on, definitely work on more of those, and just know that those equations are basically a fixed concept in physics. I don't expect you to memorize them. Just use them. You've got the equation reference sheet. Just use those and you can never go wrong. Always list out your given variables. Take a look at what is known. Ask yourself, from what is known, what can be inferred from that. And then if you only have one variable missing, then it's simple. You just do that one, you just solve for that one equation. If you have multiple variables missing, 2 or more, that's the first thing that tips you off that, okay, I'm probably going to have to use multiple equations, more than likely merge equations together so that I can get the variables that I have, I can use them and substitute this entire equation for this one part of the variable. And before you know it, we're deriving out these longer equations that serve our purpose. Hope this helped. Practice those problems. Stay curious. I'll see you in class. I'll see you in the next video. It's always good talking with you. Bye.